Okay, everyone, so let's continue with the session. This is part of the contributor talk session. The first one was in the morning, and this is the second part. And this is Ari from Boston University, who is going to talk to us about the limits of provable security against model extraction. Thank you.
Yeah, thanks, Daniel, and thanks to the rest of the organizers. So this is based on a couple of papers. The first is joint with Ron Canetti, and both you can find on ePrint. So in a model extraction attack, an adversary interacts with some interface to a machine learning model in an attempt to extract the model itself. So in this case, what I mean by that is the adversary will make some queries, obtain the labels, and then try to output some classifier that agrees on most of the points with the underlying classifier in the cloud. So why steal models? Well, first of all, confidential and proprietary models are often offered as machine learning as a service, where the owner charges on a per query basis. So anytime the client can infer some points or infer some labels at points it has not yet queried, then it's kind of extracting some value away from the owner. And then second, I think maybe more interestingly, model extraction can be seen to decrease security and privacy, especially with respect to model inversion or adversarial example attacks. So for example, Biggio et al. Show how to find adversarial examples in malware using model parameters. And Fredrickson et al. Show how to do image reconstruction from a facial recognition model in this white box setting. So how do we defend against these model extraction attacks? So one thing you could do is inject noise. You could do this either independently per query, or you could even modify the underlying model deliberately. And the point of this type of defense is to limit the amount of information that's revealed per query. And it indeed does make it harder to extract, but it's unsatisfactory for some very important applications, like, for example, when accuracy is critical, so autonomous driving or medical diagnosis. Another thing you could do is use cryptography, and there's a bunch of proposals based off of secure function evaluation. So in secure function evaluation, Alice, the model owner, and Bob, some client, would be able to jointly compute the output of the model on Bob's input in such a way where Alice would learn nothing about Bob's input and Bob would learn nothing about the model, but crucially, nothing beyond what is revealed by the output of this joint computation. So this is great for secure function evaluation, but it's not sufficient for model extraction because we don't get any guarantees for the case that Bob is allowed to repeatedly interact with Alice, with the model owner, and build a large data set to then infer from. And similarly, program obfuscation doesn't fully solve the problem because it also preserves functionality. And the point here is that basically the ideal world in these cryptographic solutions is insecure against model extraction. And this was pointed out by Vinod, by Kuntanathan in his talk at this workshop last year. So a third type of defense, which is going to be the focus of this talk, is what I like to call an observational model extraction defense, or OMED for short. So in an OMED, the server who holds the model or the model owner would take the queries, which are requested by the client, and forward them to some kind of analysis algorithm, the OMED, which would then output either accept or reject. And in the case of acceptance, then the OMED would advise the owner to forward the labels back to the client. And on rejection would say, server, ignore the client. So the point of this OMED, which many practical instances exist in the literature, is, and it's often cited, that The point is to determine if a client is acting adversarially or benign. And I'm not going to talk about all the plenty of different instantiations that exist in the literature. They work well in practice, and they use very different techniques. But what I will say is that they're all kind of boiled down to efficient statistical tests on client query distributions. And despite working well in practice and being very lightweight, they don't have any known security guarantees, at least not the type of provable security guarantees you'd expect from a cryptographic solution. So that being said, it's not really clear how to even define security for this kind of problem. So you could try something that's zero knowledge style. But really, this is too harsh because at the end of the day, the client needs to be able to learn something about the model. You know, in the example of machine learning as a service, otherwise the client may just not use the model if it knows it's not going to learn anything going into it. So something more realistic, which is a little weaker, is maybe the guarantee that the client learns nothing beyond what can be efficiently deduced from some random examples about the model. So this is a bit more interesting. And I think my point is that thinking back to the OMEDs, what they're really trying to do in this paradigm of acceptance versus rejecting is to confine the client to some specific distribution. And so really one can see that implicitly the OMEDs are already using this type of security model, and the OMEDs themselves are used to kind of enforce this type of paradigm. So how can we actually get something related to making extracting models hard out of this? I'll think of a client as one who just picks some distribution over queries. And in this case, the OMED is basically a distribution tester for some kind of honesty property. So kind of inspired by interactive proofs, something we might want is completeness, which is when honestly distributed queries would be accepted, and soundness, when adversarially distributed queries would be rejected. And here, so I'm still thinking of this abstract honesty property as some kind of, or some subset of all distributions over the input space. So once we have, if we were to have complete and sound OMEDs, then the question that remains is, well, how do you choose P? So we want something that makes the distribution, or we want some kind of distribution that makes extraction hard. And I argue that the natural thing to do is to use hardness assumptions about pack learning to pick this distribution. So what we can obtain in our work is a type of provable security lemma where if we have a complete and sound OMED and we're willing to make some hardness assumption about pack learning, then you can show that when the models come from this, the underlying model comes from this class, then it's basically cryptographically hard to extract it. And the intuition here is that when the client queries honestly, then the model is protected by the hardness assumption. And on the other hand, when the client queries adversarially, then the model is protected by the soundness of the OMED and the fact that in that case, the adversary never would have seen the labels. So can we actually build these OMEDs? After all, we're competing with some practical lightweight instantiations that are very efficient. And so the main result in this work is that the answer is no. No efficient OMEDs when the model is a decision tree, and that's assuming that the learning parity with noise assumption holds. So the way we prove this is by making a connection to the covert learning model from the first paper. So in the covert learning model, the kind of situation that we're entertaining is when a learner is working in the learning with membership queries model, and with a twist. So the learner is allowed to query some function to try to obtain an approximation. But at the same time, there's an adversary who is viewing all these queries and responses. And the game for the learner is to have a pack learning guarantee as usual, but also prevent the adversary from learning at the same time. And so the way this is formalized is using the simulation paradigm. And basically the guarantee that the learner wants to achieve is that the transcript over the queries and labels is efficiently simulatable using only random examples to the function. So this is often seen kind of in a qualitative sense to be much less information than full Oracle access. And so the idea here is that the covert learning algorithms basically fool the OMEDs. And this is seen concretely in the case that you have some kind of, or some complete OMED, then it must have very bad soundness parameters. And that's because the covert learning algorithm can essentially extract the model from using a query distribution which has the adversarial property, but is computationally indistinguishable from distributions that have the honesty property. So in that case, what happens is that despite the client acting adversarially, from the perspective of any efficient OMED, it will not be able to basically classify it as adversarial or benign. So assuming that the OMED accepts a large percentage of honestly distributed query sets, then it must also accept with high probability this adversarial distribution. So the point is here that our provable security lemma required complete and sound OMEDs. So if you believe in the learning parity with noise assumption, then you can instantiate that lemma. And yeah, I also want to mention that in his talk last year at this workshop, Vinod kind of dreamt up this scenario, and he actually came up with an attack that I think at the time wasn't known as a covert learning attack, but it was, where the advantage there was that actually the attack worked against unbounded OMEDs because the query distribution was statistically indistinguishable from random. But on the other hand, it was working against a much more contrived set of machine learning models, being noisy linear equations mod Q. So ours is the first that's working against a much larger kind of practically inspired class, being polynomial sized decision trees. So I think in the interest of time, I'll stop there. But I want to encourage people to approach me to talk about any of the many different interesting directions that arise from here. Thank you.
Thank you so much. Other questions for Ari? We definitely have time for questions. So I would like to ask you a question. You talk about all these different defenses for model extraction, and I understand that we don't have provable security guarantees for them, but let's say that we are confident that certain solution is secure enough. How, let's say, for instance, in the context of secure multi-party computation, how MPC friendly they are? Because at the end of the day, you need to implement it in that box that does secure things. So if they are super complex, it's not going to be super efficient also.
Yeah, that's a great question. I'm not sure I really know the answer. So I think when it comes to the practical OMEDs that I kind of briefly cited on the screen, they're, from what I can tell, they're pretty lightweight, and they kind of work just on top of if you think of like a machine learning as a service scenario, they work just directly on top of the model. So it's almost like you can think of it as like a third-party algorithm. It doesn't need to interact at all. So yeah, I don't really know the answer, but
you were talking, for example, about checking the Hamming weight of the inputs or stuff like that. Like this is a non-linear operation that in the light of the whole model may not be that bad because the model already is quite expensive to compute. But if it is a super, it involves exponentiations and so on, like it may not be very good anyway. I mean, it does not,
Yeah.
but like I'm just saying.
So if I remember correctly, so the Hamming weight is referring to testing the Hamming distances between queries from the clients. So that can happen prior to any evaluation on the model. If I understand your question correctly, so
No, but like if you have, for example, a machine learning as a service system, and you have 3 non-colluding servers who are going to maintain the system, they have to check the validity, or they have to check this P property from the input client, and the input is going to be secret, right? So you cannot see what the input is, and you need to do this check securely.
Yeah. Okay. So this a misunderstanding. Yeah. In this case, so I mentioned secure function evaluation, which has the guarantee that Bob's input is not revealed. I think normally when it comes to model extraction, we're not really caring about whether the input is revealed to the server. So, but if your question is, do those things work together? That's a good question. I don't know. That would be a good thing to look at. Yeah.
Any question for Ari? Please repeat the question.
So it works. The decision tree, the model itself doesn't need to be coming from any distribution. So the model can be any decision tree. You might want to make a hardness assumption, which is average case, so that you can get a guarantee that most models are hard to extract. But the actual machine learning model that needs to be extracted can be adversarially chosen. On model extraction, I won't recommend a specific survey, but I think that all of the talks on specific, especially the defenses. So there's a ton of attacks, papers on attacks, and they will all, any talk or any paper, the introduction, I think would do great. Yeah.
Okay, so let's thank Ari again. Okay, and the next speaker can come kindly. Thank you. I also want to quickly remind the audience, this morning we had to omit the first talk, and the speaker is actually available, so we're going to make a slightly longer session today at the end to accommodate for the first talk.